Yeah, you can proceed, please.
Okay, like this is next slide, yes?
Yeah.
Okay. My presentation is about the perspective of scanning polarization lidars for retrieving the orientation properties of atmospheric aerosol and ice crystals. So ice crystals are typically has oriented crystals, and we can confirm it by the eyes because we see such a beautiful phenomena like halo or sundogs or something extra. So it's important to take into account the orientation of these crystals. But most often scientific research made with the suppose that the crystals in the clouds are randomly oriented. And usually we use lidar to understand what's happening in clouds and what is the microphysics of these clouds. And so we need this solution for light scattering, problem on ice crystal, because we need it to first to interpret the lidar data. And because there is no such a solution today, the complete solution for ice crystals, it's hard to interpret the lidar signals when you sound in cirrus clouds. And also we need this solution of light scattering by ice crystal of cirrus clouds to make the radiative transfer, to solve the radiative transfer problem. So there are several methods to solve this problem. The first group of this method is so-called exact numerical methods, rigorous methods, such as discrete dipole approximation, FDDT, invariant embedding, and also. So all these exact numerical methods are very good, but they are fits only for small particles, like dust particles. But it's problem to calculate the ice crystals because ice crystals much larger than wavelengths, and we can apply this numerical method to solve this problem because of computational issues. So other interesting method is geometrical optics approximation. This geometrical optics approximation is also very good method to light scattering on a huge crystals like a ice crystal, but unfortunately it can be applied to lidar application, because in the backscattering, which is crucial for lidar application, there is a Hungarian backscattering phenomena, and geometrical optics doesn't take into account the diffraction and interference phenomenon, so it can resolve this coherent backscattering enhancement, and so we cannot apply geometrical optics approximation for cirrus clouds, especially for hexagonal ice crystals, where there is a huge this geometrical optics produce a huge singularity in this case. And the most suitable method is the physical optics approximations. The physical optics approximations first developed by Borovoi in Tomsk, and then it had been reinvented by Dr. Pinyan in USA and Professor Lei Bi in China. So it was it is a very useful method. We can apply it for physical optics for light scattering on ice crystals, and I will show you how it's works, this physical optics method. So before we start from physical optics, I just briefly introduce the exact numerical methods, finite element methods. So the idea is to discretize the whole integration volume by the finite mesh, and then solve the light scattering problem on whole medium. So there is a fine difference time domain method, the same idea. So you have to discretize this by the small mesh, and then bigger the particle, then more mesh you need and more computer resource you need. The integral equation method, the discrete dipole, like a discrete dipole approximation. So you discretize the particles with final domains, with final structures like dipoles, and also needs more computer resources when the bigger the particle is. And the thematic approach is very good approach. It's very suitable for large particles, but it's based on the spherical function. And if the particles is non-spherical, such as ice crystal, you can apply that. But there is an invariant embedded matrix methods. It can be applied for such a crystals in theory, but you have to slide the particle on this huge number of the slices of the like a onion model, and there is a lot of piece of this onion, and so it's also computational resources consumption. So all exact numerical methods are not applicable when talking about the large particles like ice crystals. So the geometrical optics approximation, which is shown here, so it's like a ray tracing technique, so based on the geometrical optics methods. And if there is a light beam goes to the one direction, it is like a ray, like a dot. It's singularity here. But in reality, what we see, if there is a light coming from the reflected from the, for example, this facet, we see diffraction pattern, and that is why the geometrical optic doesn't take into account this diffraction phenomena and also interferential between these optical beams. It can be applied for LiDAR application, because this is a very crucial for this idea. But what is the physical optics method? The idea of physical optics method is that first, we suppose that there is a plane parallel wave just falling on the crystal. It's reflected and refracted, for example, like this. This is a reflected beam. Someone is refracted, goes into the crystal, then goes out. And then we suppose that, and then we suppose that this kind of beam, we knew this shape, goes to the diffraction. So we calculated the internal field, the internal scattered field within the geometrical optics approximation, and then map it to the far zone with the diffraction taken into account. Okay, this was the idea of the method, but what the Lidars measures? We have to calculate the Lidar scattering, not this just, we have to solve the light scattering problem to Lidar, so we have to understand what the Lidar measures. Usually Lidar measures the stock parameters, not the electromagnetic field. So we have to transform this electromagnetic waves equation to the Stokes parameters. And if we are just concerning the electromagnetic scattering, the usual task, we suppose that there is electromagnetic field, incident field, and there is a scattering field, and there is a 2x2 amplitude matrix that can transform this incident field to the scattering field, incident field to the scattering field, and is usual solution, but not very good for LiDAR applications. And if we are talking about LiDAR application, we goes from this 2x2 amplitude matrix, goes from this S matrix to the matrix 4x4 phase matrix. It's so this matrix can transform the Stokes parameter of incident wave to the Stokes parameter of a scattering wave. So this is what LiDAR usually measure. So the intensity, the depolarization, polarization. So if we are talking, if we get solution in term of Stokes matrix, it's very useful. So it's not only important to just have a solution in this way, but also important to represent the solution in this way, because it's more suitable for LiDAR applications. And this matrix, scattering matrix, has some interesting phenomena. And if we are talking about the light scattering on a small or circle particles, spherical particles, so the forward scattering is like this matrix. So it's just completely, for example, for homogeneous optical and active and spherical particle, it's just completely completely simple matrix. So it's just like unity matrix with some a scalar component here. So this is why we usually suppose that we do not need to calculate the exact forward scattering matrix for small particles. But if you are talking about the cirrus clouds, you also have to suppose that the forward scattering matrix is not very easy, very simple. But if you are talking about this backscattering matrix, it's just complicated. It's more complex like this. For randomly oriented inhomogeneous spherical particles, also unity. But if the particle is not spherical but randomly oriented, we have this matrix is not the identity matrix. So this is why we have the depolarization ratio. The polarization ratio is here. So the physical optics methods. What is the idea of the physical optics method? The brief geometrical interpretation I show here, but what is the basis of this? So first we suppose that there is a Maxwell equation, and we can rewrite this Maxwell equation in this case using this dyadic green function conditions to this. So first we suppose that this volume integral is equal to this surface integral. So we can evaluate the electromagnetic field outside the particle if we have solution on the particle surface. If we have this exact solution of the particle surface, we can integrate it and find the volume integral in the electromagnetic scattering on every point. But of course, usually we can find, so this is a solution. So here is the integral equation over the particle surface. This is a volume integration over the source of the sources, like here. So usually it is not completely easy to find the solution on the exact solution on the particles here. But if we just find the idea of the method is to find the approximate solution on this surface, particle surface. So it's a scattering field here. It concerns only, so incident field is from this volume integral and scattering field from this surface integral. And we need only the surface integration to understand the solution. And the base idea of the physical optics approximation is that we do not find the exact solution on the particle surface. We find the geometrical optics approximation. We use the geometrical optics approximation to find the approximate solution on the particle surface. And because the particle is very small, but larger than wavelength, and then because the distance that the light travels are also small, we can assume that the geometrical optics solution works well for the particles larger than wavelengths. But then we can apply the geometrical optics to find this solution. And if we do this, we can use this integral to find the solution over the all scattering direction in the far region. So this is the idea. And we have three different scattering approximation here, and also three different scattering theory in the far field. But in we are talking about this really far field, we suppose this approximation and we for far region, and we understand that all this scattering produce the same result. And so we just transform this scattering over all this particle surface to like this. So all this scattering field can be integrated not over the whole particle surface, but the electromagnetic field on every facet is produced by every beam. So instead of the integrated all the surface, we can integrate it only the optical beams. And this, if we do so, it's just mathematically the equivalent, we see this, that the idea of the physical optics is that we use the just Kirchhoff diffraction integral for every beam. So the how to say, the physical idea of the method is that we calculate the light scattering beam, and when this beam is going out of the crystal to the far zone, it's just going through the Kirchhoff diffraction theory. But mathematically, it is the equivalent that we just calculated all this surface integral phenomenon, surface integral. So this is the base idea. Instead of to integrate all this electromagnetic field on all over the particle surface, we integrate the electromagnetic, we integrate this integral over the all this optical beam. So because we use the beam splitting technique in our physical optics method, it allows us to fast receive the solution. So it's like this. So there is a one plane falling on the crystal. If it is just reflected, it goes through the diffraction. If it's go inside the crystal, then go outside the crystal, it also goes to the diffraction phenomena. And also we take into account the interferential between this wave. So it's easiest and absolutely simple physical ideas is supported by strict mathematics. And we see when we got this physical optics methods. So how is the solution looks like here? For example, this is the whole scattering direction. This is the back scattering direction. This is a forward scattering direction, whole scattering directions. And this is the first iteration. And we see only the speckle, only the shadow diffraction here. But then we put the one internal reflection, so it's a specular reflection. We see the reflection pattern of hexagonal pattern here, for example, this rectangular patterns here. Then we add more interactions with light, so like this, and also we receive the full solution. And this is a solution obtained by the physical optics method, the duration process. And this is a solution obtained with strict exact methods like ADDA solution. So it's very complicated, very consistent, this solution for this, for example, particle. And then the bigger the particle is, then more accurate the solution is. So it is very important to make the solution for huge particles. So this is, for example, how the solution looks like when you rotate the particles. And it's a small particle, and you see this diffraction patterns. But when the particle is more larger, the structure is more complicated, and you have to rotate the particle more precisely to integrate all these phenomena. All these optical properties have to be integrated. All these peaks have to be integrated to have a good solution. What's happened if you use small number of orientation, like here for 50 micron particles is a typical for ice crystal, and you use only this 32 angle discretization of the direction sphere. It's some solutions like this, 64, 100, 200, 500, and 1000. So you have to use the 1000 discretization of scattering sphere to just represent this this diffraction pattern. And you also have to use enough of orientation of particles. For example, like this, for size parameter of 100, you have to use about 200,000 orientation of the particle to receive the solution. You can't use any exact methods, because the exact methods takes hours to just receive one orientation, but you need thousands of orientation. So only the physical optics method can provide this solution. And this is how this convergence of the iteration process here, of the orientations here. And we see that the solution is converged with our estimations. And also it is important not only for intensity, it's how the intensity looks like when you use not sufficient amount of the orientation. Red is the sufficient amount of the orientation. And how it's used the polarization elements. So the polarization elements are more isolated function that you have to calculate it, especially in backscattering direction, very precisely for lidar orientation. So this is amount of number of orientation, how many orientation you have to use for such a phenomenon. So typical is about 1,000, the size parameter of about 1,000. So it's several billions orientation you need to use. And we do this. And we do all this calculation, all this integration, and we receive this solution for hexagonal columns, for hexagonal plates, for some of the dust particles. So we use this data band for hexagonal particle from 10 microns to 1,000 microns. So we cover all this entire range of optical properties and of cirrus clouds, and we got these solutions. And we also compared this solution. This is our solution, the blue line. We extended for the small particles, and this is the exact numerical solution. And we see this very good agreement between the exact numerical methods, our physical optics approximation. And we see this, for example, relay scattering here and geometrical optics regime here. It's not the geometrical optics solution because the geometrical solution is a little bit lower because it can't produce the backscattering enhancement, but it's geometrical optics regime. It means for the particle which size is bigger than 1,000, you just double the size, you just 4 times multiply by 4 the solution. So it's just like very, very easy to calculate the solution for large particles here. And also, when we are trying to find a solution for some dust particles like these regular shaped particles, we have to understand that it's not enough to have a solution for one just particle like this, because these 3 particles has a completely different solutions, especially for lidar application, at 10 times different. But which one you have to represent, and we calculate 300 particles and then find the average solution for this. So this is the average, so it can represent the cloud of dust to represent the light scattering. And so you have to always use the large amount of the different particles to represent some shape. And all these particles have this backscattering enhancement. If you are talking this solution, just for example, is within the geometrical optics solution, there is no backscattering enhancement. But if you're using the physical optics methods, you see the backscattering enhancement here. It can be just 2 times bigger than geometrical optics solution, and the depolarization ratio is different here. So this, for example, we explain why we have this this backscattering enhancement phenomenon, and we have calculated precisely. And this what the lidar sense, and this what the geometrical optics says. So it's different. And also this interference depolarization phenomenon. So it's a negative depolarization phenomenon here. The depolarization, just here, the deviation of depolarization. So it's the same for ice crystal, where the ice crystal is a perfect shape, like hexagonal shape. So the geometrical optics give us a singularity, just singularity. But because of diffraction effect, the physical optics provide us with a finite solution like here. And to compare, this is the backscattering enhancement of a regular particle. This is the corner reflection effects, which provides the infinite intensity in geometrical optics. So this is a backscattering enhancement due to this corner reflection shape. So it's a comparable here. But all that I told you before, it was a very hard task to receive the solution for random orientation. And but what I wanted to say that we do not assume that particle in cirrus clouds are randomly oriented. Sometimes they are preferentially oriented. And we have to calculate this whole task to, in case that the particle is not randomly oriented, but preferentially oriented, we suppose that the horizontally oriented particles like this, so plate try to align the horizontally like this, and ice crystals hexagonal column try to align it like this, so with this B angle. So we call it flutter, so the angle of the inclination. So it's a flutter is 0, it's just completely horizontal plate. It's a flutter is about, it's a huge, so it's close to the randomly orientation. So usually in cirrus, the flutter is about 3 degrees or 2 degrees or something. That is why we also incline our our lidar just incline from vertical, like Calypso is just inclined so 3 degree. There are a lot of lidar just not absolutely vertically, but 3 degree, because the typical flutter is just less than 3 degrees, and we have to calculate it. So how the solutions looks like? So just imagine that the lidar just sounding the cirrus particle. So first there is a specular reflection with huge specular intensity. When the particle is just a little bit slope, so this diffraction phenomenon, specular reflection goes in different direction. So, and we see this huge specular reflection here for small angle of flutter. And then appears this corner reflection for hexagonal particles. And we see this strong corner reflection here and some process here. So this is a typical solution for oriented hexagonal plate. So there is a specular reflection when it is horizontal, and there is a corner reflection when it is randomly oriented, or if it is oriented with a huge tilt, huge flutter here. The same is for hexagonal column, or usually, and we first suppose that it's a normal distribution, that the probability of the flutter of the orientation is by the normal distribution. It was our first guess, and we did a lot of calculation in this way. So this is a probability density function here. So when the lidar sound in the crystals, the slope lidar, we also sometimes we see the specular reflection and 3 type of corner reflection. All these phenomena have to be taken into account. So this is a solution. So this is a flutter. This is a lidar angle. So what's happened when the lidar, scanning lidar, sound in the completely horizontal oriented particle? We see this huge specular reflection, then the intensity goes practically to 0, and then it enhances a little because of the corner reflection, and then 30 degree appears the next kind of corner reflections. So this appears first, this appears the second, and about 30 degrees like here. So this is the waveguide phenomenon here. So this is a typical. When the particle is randomly oriented, plus here, it doesn't really matter which angle the lidar is sloped. So if you sound in the randomly oriented clouds, you can slope the scanning lidar and you see the same. But when the particle is horizontally oriented, you see completely different. And this is the intensity. Intensity not usually good for interpreting for microphysics, because there are 2 unknown. This structure and the density of the crystals in the clouds. And because you don't, you can't differentiate if this intensity goes down because of the particle orientation or because the clouds just has a different number density of the particles inside the clouds. So we use this polarization elements of Mueller matrix like M12, which refers to the polarization phenomena, M22, which refers to the depolarization phenomena, and also M33, which refers to circle, M34, which refers, and M44, which refers to circular polarization like here. And this is the depolarization ratio. It's a little bit unusual results, but because we rarely find it in the real nature, but if in real nature there is a clouds of completely horizontally oriented, just consist only from the plates, we see like this. So zero depolarization ratio before 30 degrees and then high depolarization ratio on the 30 degrees. But in nature, we also has the mixture of this kind of crystals, like randomly oriented crystals and horizontally oriented crystals. This is why we can see this in the nature, but the models show us this, and it's very useful result. We can use it with interpretations later. So this is the Lidar ratio, and Lidar ratio is more informative about the flutter because it doesn't, it hasn't contain the particle density in the clouds here, and it can show us the flutter here. And how it is the variations. So this is a Lidar ratio versus the different flutter. So if a flutter is 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, and 10 degree, and you can see that you can use a Lidar ratio to differentiate the flutter. It in case of the size of the 30 micron, if the clouds consist only the one particle with 30 microns, the monodisperse clouds of the particle with 30 microns. But what happens when you use different sizes, 30 microns, 100 microns, 300 microns, so three different sizes, and you see that the Lidar ratio changed the intensity, but the place where it's gone from 0 to some value is the same. So you can use this position of Lidar ratio to understand the flutter, even if you don't understand the particle size distribution of the clouds. It is very important because usually you don't know the exact particle size distribution of the clouds, and still you can use this Lidar ratio of scanning Lidar to understand the flutter. Also, it doesn't really matter which wavelengths have you used, the blue, green, or red, because it is still, the particle is still much larger than wavelengths. The phenomena is the same, and you use whatever you want wavelengths, and the result is practically the same. And also, what happens if you use the mixture? It is very interesting. If you in nature, we also see some mixtures, and the clouds, there is some randomly oriented particles and some amount of horizontally oriented plates, for example, like this. And this black goes to the proportional is 0, so only horizontally oriented clouds, and we see this phenomenon. And then we add 10% of randomly oriented particles and 50% of randomly oriented particles, and we see that Lidar ratio can evaluate the flutter of crystals even if there is a mixture, even if the cloud consists of 50 by 50, 50% of hexagonal oriented particles and 50% of randomly oriented particles. And also this is for intensity. In very ideal situations also the same, but of course we suppose that the concentration of the particle in cloud the same, but usually it's hard to find this experiment. But if you manage to find the way, the case when you can scan in the clouds and you suppose that the clouds is the same, the concentration of the particle is the same, you can use the intensity to understand the flutter here. And the depolarization ratio. What is very interesting is the depolarization ratio, and usually people refer to depolarization ratio, and it is very easy to measure it. So there are three cases. So there is the completely randomly oriented particle. Some of the particle with depolarization ratio 0.4. So it's a one case, a completely different, completely randomly oriented particle. And if you just sensing it with lidar, if you scanning lidar, nothing change. Then this black is just the cloud consists of absolutely horizontally oriented particle, and it gives us depolarization ratio 0 if you scanning. But if you get the mixture of them, so 10% of oriented particles, 90% of randomly oriented particles, and you send this depolarization, it's first 0 because of specular reflection. Then it goes up because of randomly orientation particles influence. So you see something like this. And the position of when it happens also tell us about the flutter. And if you got this 50 by 50, so 50% of the horizontally oriented particles, 50% of randomly oriented particles, you usually see some depolarization ratio like this. So first it's 0 because of the specular reflection, then it goes to some value because of these randomly oriented particles. And the position when it happens also refers to the flutter. So then bigger the flutter, then bigger the position. So usually it's like this, about 3 degrees, so flutter is about 1 degree. Then what we did, we evaluate.
Sorry to interrupt you. We have 5 more minutes.
Okay, we are going to close. So what we do next, we evaluate how the different shapes influence, and we have 6 different models, and we calculate all these models. So a lidar for scanning lidar like this. And we see all this model produce this backscattering depolarization ratio on 30 degree. But when you use this mixture, the depolarization ratio of mixture 50 by 50, so we see this specular reflection and then this depolarization phenomena here. And we made this experiment to compare our results. We use the scanning lidar of Institute of Atmospheric Optics. It looks like this, so it's a scanning lidar. And we see some experimental results like here. So the dot is the experimental results. The line is our fittings. And we see that sometimes our experimental results fits well to the theory fits well to the experiment, and we see this 32 degrees enhancement of the polarization ratio here, and we see the specular reflection here, but sometimes it's not goes very well, but also suitable here, and we can evaluate the microphysical phenomena from this. So we can evaluate that this, for example, can be 20% of the plate with flutter 3 degrees and randomly oriented columns and randomly oriented arbitrary particles with this proportional. Or here is just a particle with here is with a very huge flutter or something. But then we can see that very interesting phenomena with the experiment. Sometimes we see that, so this is a scanning, and scanning lidar just scanning the clouds, and we see that some clouds consist the oriented particles. Sometimes some clouds consist of randomly oriented particles, and we see that this signal is changed, this not. So like this. And also we evaluate this, we'll do a lot of experiment and find out that this is the experimental observation, the dots, and this is a scanning about 4 degrees scanning, and this is the intensity. And we see that our guess that the particles orientation flutter obey the Gaussian distribution, so normal distribution law, it's not very good. If we use the exponential distribution, it fits very well. So it is very important because as far as I understand, no one supposes that it is exponential distribution. A lot of scientists suppose that this is a Gaussian distribution, but we got the experimental evidence that it's better to use not Gaussian but exponential distribution. So for my presentation, it's all. So what we have the physical optics methods, which can calculate the light scattering problem for scanning polarization lidar. In case of preferentially oriented ice crystal, it's a unique solution. And we also see that scanning lidar is a very prospective tool to retrieve the information about particle orientation. And you don't really need to know a priori the size distribution in clouds and the concentration of the clouds, of the particles in the clouds. Even you don't understand this, you can understand the particles orientation using the scanning lidar. It is very important information for a radiative transfer problem. And also, what we understand that there is no enough experimental data of scanning lidar sensing of cirrus clouds, and it's very crucial. And I ask you to focus on this scanning. And first, small angle scanning to determine the flutter law, the large angle scanning to determine the shape of the particles, and sometimes we need azimuthal scanning to check if there is an azimuthal orientation or only the horizontal orientation. So thank you very much. Any questions, please?
Yeah, thank you, Dr. Konoshonkin, for your very excellent presentation with beautiful graphics and animations. The animations were very impressive, showing the ice crystal formation and evolution. Yeah, thank you very much. And there is a question by Dr. Madhavan. His question is, can we estimate the refractive index with polarization channel option in a LiDAR?
If we are talking about cirrus clouds, of course not, because cirrus clouds consist of water ice, and water ice has practically zero imaginary part, so of refractive index. But if you are talking about the imaginary part, so it's impossible. But if you want to find the real part, it's obvious that for cirrus clouds consists of ice crystals, ice is just about 1.3. But if you are talking about the dust particles, yes, it's possible, but you have to use several wavelengths, but not only the depolarization ratio, because the depolarization ratio more sensitive to the particle shape rather than the particle refractive index, because the particle is very large.
Thank you. And one more question by Dr. Jayesh Lal. How we can accommodate the multiple scattering effects?
Yes, it is very useful to take the multiple scattering phenomenon. And we have to, in this presentation, I was focusing on the cirrus clouds, and cirrus clouds are usually optical fix. And because they are very optical thickness very low, thickness is very low, we can negotiate the multiple scattering. When we need, we do the multiple scattering, because we has the solution for all scattering direction and the back scattering, and